the laws of reflection and refraction. So when light interacts with an optical medium, three things happen. One here is that the incident reflected and refracted ray all lie on the same plane. I mean, this is a remarkable fact. And when you look at Maxwell's equations, it's like it pops out like instantly. So let us define two things here. Okay, the first thing is that we have two transparent mediums. So what I need here is that I need a boundary. So here's my boundary. Okay, so this is my optical boundary. And in fact, I think I'm going to move this over so that I have the ability to write. So I'm going to move this over right here. And so what you're going to see here is that the first thing that I would say here is that I have transparent mediums are identified via the index of refraction. I'm going to move this over again. About right there. Now, how am I going to identify these? Well, what I'll do here is that I'm going to say that this is one index of refraction. This is one optical medium. And we use this thing called the index of refraction. So what we say here is that we say that N1 is the index of refraction for the yellow one. And that's a property material. And then I have a second index of refraction right here, which I'm going to label N2. So now I've separated these two materials with that boundary here. Now what we find here is that all angles are measured relative to the normal. So it's got to be normal to the surface. So let's say that this guy right here, this is the normal. Now there are three rays. So the three rays are the incident. So when I'm looking at the incident here, this guy's coming in. Let's say it comes in like this. And this guy is the incident. And we measure this relative to this angle, theta 1, relative to the normal. Now, this incident ray does two things. One, it reflects. This is the reflected, and I'm going to call this angle theta 1 prime. And right, so now we have a reflection. And then finally, we have a second ray that it refracts. So this is the refracted ray. And here you can see that this is the angle that we measure here, and I'm going to call that theta 2. And so then I have a refracted ray. So now that's one. So all of this occurs in a plane. So then I have two laws here. We have the law of reflection. And the law of reflection says that the incident angle which I call theta 1, is equal to the reflected angle. In this case, it's theta 2. So that's our law of reflection. So the angle that it comes in must also equal to the angle going out. And I see I have a typo here. This should have been 1 prime. And then finally, there's a second law. This is known as the law of Snell's refraction. A lot of times people call it Snell's law of refraction. It's really just the law of refraction. And it says here that the index of refraction of one medium, which is a property thing, times its angle, theta 1, the sine of that is equal to n2 sine of theta 2. Most of our time is going to be spent with the law of refraction. So now what I really need to do here is that we want to spend all our time effectively on the index of refraction. That's what this chapter is primarily about. So that means here, now what we want to do here is that we now want to look at the interpretation of the index of refraction. And the way we write the index of refraction is we define it by the symbol n. So you'll see here is that we're definitely going to spend the most time on this. So to give you an idea of what the index of refraction is, I want to start with an analogy. And this analogy is going to be a lawnmower. So what do I know? So how do I start to talk about the index of refraction? The index of refraction, which I primarily call just the index a lot of the times. So the index is proportional to how the wheels of the lawnmower interact with a surface. And in this case, we have grass versus concrete or sidewalk. And here's what we know. The index of refraction of the grass is larger. Why? Because the wheels, they interact more. So there's more interaction between the wheels and the grass. And as a consequence, there's a slower speed of the wheel. On the other hand, N of concrete is smaller. And the reason why it's smaller is that there's less of an interaction between the wheel and the concrete, and so therefore the wheel moves faster. So it has a faster speed. That right there is the core of the index of refraction. It explains why the light ray is going to bend or refract. So now what I want to do here is that I'm gonna let's look at a mower here. So you could imagine that I'm gonna have a wheel right here. Oops. Let's say that here's my wheel, and here's my wheel here. And then I'm gonna have a wheel here, a wheel here. So when I think of my mower here, I could imagine that it's gonna look something like this. Then the mower typically kind of kicks out. It comes in, gonna kick out, comes in, and then I have the front. So then the front may look something like this. So then you can see here is that this is my wheels. This is the, by the way, but we need the top of the mower. Let's say that this is the top of the mower. So then if I start to look at this guy, then I could start to say, well, this is my mower. And it's going to be going to the right. And we know that the mower is going to be going along the boundary between this guy right here, right? So when I look at this guy, here's what I see. Up here, this is going to be concrete or sidewalk. So then this will be my gray sidewalk right here. On the other hand, this side here is going to be my grass. And so here's my grass. And so therefore, if I look at N of concrete, and this is N of grass, what do we see here? I'm seeing that this guy's going to do what? This wheel interacts more, so it's going to be slower. This one is going to move faster because it's on sidewalk. So what we say here is that the mower bends. Let me be careful. Bends. In other words, it refracts downwards more because the speed on concrete is greater than the speed on the grass. So what I want to do here is to show you this. I'm going to show you the Fent applet, which is listed on wave refraction. And you'll be able to see this using the applet. So let's go to that thing. Okay, as soon as I get this, so here it is. So let's resume this thing. So you're seeing light coming in from the here. So now that's traveling at medium 1 speed. Okay. Medium, the index of refraction of 2 is larger than the index of refraction of 1. You could see that 2 is 2, 1 is 1. Now look what happens here. I'm going to start taking steps here. Okay. Let me do this. Oh no, I messed up. I messed up. Let me restart this. So now here it comes. And that's the wave. Okay. Now that's the speed. So that's to judge the speed. Now let's look at the second one. Now what you want to do here is that you want to look at the line of this red line right here. Now look, this line right here is the wavefront, just like this one's over here. But look how much slower the bottom one is traveling compared to the one on the top. And now look what happens. You could see the bending of the ray, and you could see that front moving slower. And that's because there's a wave speed change, which is exactly what we're seeing in this situation right here. Now note that applet's a little bit more advanced, but it still shows the what's going on pretty well. So now that you've seen that there's the speed change causes the bending of the ray, what I'd like to do here is that I'd like to look at the details of this thing. And here's what we find. There are 3 possible outcomes of light refraction. One, I could have N1 equals to N2, N2 greater than N1, and then N1 greater than N2. So let's look at those 3 cases here. So now I'm going to do the exact same thing that I did before. I'm going to set up my boundary. And so I think last time I set them with yellow and blue. So let's look at these guys. And then let's do blue down here. So this one I want to make bigger so that it's easier to decipher here. And so let's look at that. So now I got to pick my normal. Okay, so this is my normal. Everything has to be measured relative to the normal. So here's my incident ray. So if this is my incident ray, I'm going to pick my first one. My first one's going to be this red one that goes all the way through. So this is the incident ray that I'm going to start off with. So here's my incident. If there is no bending of the ray, the only way this could be true here is if N1 is equal to N2. You know what? I shouldn't have done that in blue. I should keep the same color. Uh-oh, I'm gonna mess up here. So what I'm gonna do here is that I'm gonna do this. So this is the line that says that there's no refraction. Now let's look at the second one. So if I have an incident ray and the ray bends down, okay, it bends down like this. The first thing that you should note is that this ray is moving towards the normal here. Okay, it is moving towards the normal. And so that's what we say. If a ray moves towards the normal, then this must be the case. Then N2 has to be greater than N1. So over here, we saw that theta 1 was the same as theta 2. That's what we mean by that. Now we have refraction. And in this case, this here, this is the angle theta 2. And when you look at theta 2, it's clear here that theta 1 is greater than theta 2. So we then say that it bends towards the normal. And that tells you that you're going from a low to a high index of refraction. On the other hand, I could have a different ray. And in this case, this ray, instead of bending down, actually bends upwards instead. And so you're seeing that this ray, instead of going towards the normal, it's moving away from the normal. Since I already have light blue, I'm going to go get a different color, maybe a darker one, and then I'll highlight this to show you that I'm moving away from the normal. So in this scenario here, we then say this, that here N1 is greater than N2. So then I have to define a new angle. So I'm going to define this angle, and that angle I'm going to call theta 2 prime. That tells me then that theta 2 prime is now greater than theta 1. So all of the angles are measured relative to this. So then we say that this bends away from the normal. So once again, if the ray bends towards the normal, then you're going from a lower index of refraction to a higher one. If the ray bends away from the normal, then we say that you're going from a higher to a lower index of refraction. So to give you a sense of what's actually happening, let's do this in an applet here. So now what I'm going to use here is that I'm going to use the FET applet on refraction. Okay, so let's go look at this. And here it is. So here's the Fed applet. So what I'm going to do here is that you could see the white here has an index of refraction of air. So I'm going to move this guy. And then the bottom here shows that I've now changed the index of refraction of air. So they're both the same. So now what happens here? If I turn on the laser, you could see that there's no refraction of the ray. And that's because it's not changing, medium. The medium is the same. So a ray of light is going to go in a straight line. But now look what happens if I take the bottom medium and I start increasing the index of refraction. Look how the ray moves. So from this central line, you can see that the ray is moving where? It's moving towards the normal here, right? It's moving towards the normal. That's why I say that if the index of refraction, which here's the bottom one has a higher index of refraction than the top, and you can see here is that if I can keep changing it, there's bending. So the higher the index of refraction, look at water, look at glass here. You could see that it even bends more. So if we wanted to measure the angle of these guys, we could take this protractor and I could show you what do I mean by that. So if I align this, you can see here that if I'm at water, it looks like the angle is around 30, let's say 32 degrees. But if I increase the index of refraction all the way to glass, you could see that the angle is now about 28, 29 degrees. So it's being refracted more from that one spot. Now, let's do it the other way here. So here's where they're the same. So I'm going to move this over here for the moment. And now what I'm going to do here is that I'm going to go from a higher index to a lower index. So look what happens. Look at the ray in the second or the fourth quadrant here. Look what happens. See how the ray is moving towards away from the normal? So this guy's moving away from the normal. And so what you're seeing here is that because it bends away from the normal, you must be coming from a higher index to a lower index. So now what we want to do here is that we want to come back and we want to start looking at how do I actually do this here. And what I did here is that I found two acrylics that I want to look at the details of this thing here. So here I go. So now what I'm going to do here is that I'm going to look at refraction of light through an acrylic rectangle. Okay, and this is an important one because this is really what we're going to be looking at. So what I want to do here is that I want to break these guys up a little bit. So I'm going to label 2 points. Let me move this over here. And here's the 2 points that I want to measure. So the first point I want you to pay attention to is that I'm going to call this point right here. I'm going to call this point right here point A. And I'm going to call the exit point point B. Okay, so this point is going to be called A, and this one's going to be called B. Maybe I'm going to put the B over here. So now here we go. So this here, I'm going to look at the incident, man, I need a different color. So I'm going to call this the incident ray. And this guy over here is going to be the outgoing ray. So here I go. So the first thing that I need to do here is that I need to draw my normal. So I'm going to look at point A and I'm going to draw a normal to the surface here. Okay? And here it is. This line right here, oops, damn it. Here, let me try that again. I'm going to draw a normal. And here we go. That's my normal. Okay, so right here, that's my normal. Now what I'm going to do here is that I'm going to follow my ray. So my ray is coming in. Okay, here comes my ray. I have my incident ray. Here's my incident. And because that's the normal, this is the angle theta 1 that I would have to measure. Now what's going to happen here is that this ray has now refracted. And it's going to be moving in this direction. And because this is the second medium, I then come in and just say, okay, so this is n equal to 1. This guy in here is going to be n equals to 2. Now, what was the ray actually, what was the incident ray really trying to do? The acrylic forced this guy to do what? Deviate. So this one is deviating from this location here. And what you're seeing here, instead of going straight, it deviated in this direction. And you could see here is that that ray did what? It bent towards the normal. So therefore, if it bends towards the normal, we then say here that N2 was greater than N1. That's what we're saying right there. So then that tells me here is that this angle is theta 2. Okay, so once again, this line right here is the unrefracted ray. Now I can do the exact same thing here. Now I'm going to be looking at the outgoing ray from point B here. So now if I follow the same ray, it's coming in, right? And you can see here that now for this situation, this is the incident ray. Oh, you know what I forgot to do here is I forgot to put in my normal. So now if I look at my normal, it's going to be looking something like this here. So right here is my normal. So if that's my normal here, you can see here is that this guy is going to be my angle 1 for the situation. So relative to point B here, now what actually happens? What I need here is that I need a ray that's now going to exit, which is right here. So I'm just following the rays that are actually being shown here. And you could see that this right there, this is the refracted ray. So if it's refracted, then that angle must be measured relative to that. But look what's happening. If you look at the red line now, if this is the incident, this is the angle that it originally started as it was going through. And look what the red did. Excuse me, the blue. The blue didn't go towards the normal. It did what? It went away from the normal. So once again, you're seeing that it moves away from the unrefracted ray. So that's what Snell's law is saying. So if I now summarize this, the fact that it bends toward the normal, that immediately tells you that N2 must be greater than N1. The fact that this bends away from the normal, that immediately tells you that N1 is then greater to N2 here. And by the way, I did not label this, so in this case, I call that N1, and in this situation, I call this N2. So that's how I use the law of refraction to analyze how I'm getting either bending towards or away. So now what I want to do here is that I want to show you one more example here. And this here is a video on disappearing optically. Of glassware. Okay. So there's a link that shows it, but it's much longer. I took this video and I edited it. And here's what you find here is that if a transparent object is surrounded by another material, and typically what we're saying here in this case, this is going to be a liquid that has the same index then the light that enters does not change its path. In other words, no reflection or refraction will take place, which then implies here it appears invisible. Okay, so let's go look at the video, and here we go. And here I go.
All right, now this experiment's going to start with two containers, and this first container I'm going to fill up with water. Most of the way up, there we go. That's about right. And the second container I'm going to use corn oil, about the same amount. Now that we have these containers ready to go, the next step is I'm going to add an empty test tube to each one. We'll put one in the water first, we can see it, and I'm going to fill it up with water. And there it goes, and we can still see it very plainly. Now let's try one in the oil. Put it here. There it is. Put it in the oil. We can see that very plainly, but let's fill it up. And the test tube seems to disappear. Now let's see that again. Here we are in the water. Fill it up. There it is, plain as day. We can see it very easily. Let's try the oil again. While it's empty, we can see it very plainly. But once that fills up with oil, it seems to disappear. All right, now this experiment.
Okay, so let's go back. So the reason why it appears to disappear again is that there's no change in the index of refraction. So rays that go forward, who go across a boundary, and you could see here's an image of this guy right here, they don't change. They don't change, they don't reflect, they don't refract, and so therefore they continue to move in a straight line, and that thing actually disappears. And if you look really careful, especially if it's dirty, you're going to see that there is a residue there. So now what I want to do here is that we've been talking about the index of refraction, and we are not done with the index of refraction. So here is a more detailed look at the index of refraction. So there's definitely a lot more. And if you really wanted to get into this more, you would literally want to go into, you'd need to take a more advanced class in electricity and magnetism. So in electromagnetic wave is part electric and magnetic. The refractive index is related to the electric / magnetic characteristic of a medium. And here's what you find. What we measure is that there's this thing called the permittivity. And what this does, and we typically define this as the symbol sigma here, or epsilon, and this really tells us about the electricalness of a material. Then we have a second constant called the permeability. And this is typically with the symbol mu here. And what this guy tells us about, it tells us about the magneticness of a material. But guess what? It turns out that at optical frequencies, the magnetic part effectively drops out. It plays such a small part that we just ignore it. So when we're thinking about the index of refraction, so then the index of refraction derived from, the electrical magnetic theory reads like this. So the index of refraction is equal to the electricalness and the magneticness of a material, and that's the ratio of the electricalness of the vacuum and the magneticness of the vacuum. But because these two guys are effectively the same, these guys drop out. And so this tells us here, to a very good approximation, that it's this guy right here. So this is really, and remember, this is more of a conceptual thing. It says that the optical medium electricalness, that's what that number does, divided by the vacuum electricalness. It's the ratio of those two things. So here's what you end up finding here from when the dust all settles. So from this argument and the lawn mower analogy, and a little bit of algebra, we could then say that the index of refraction, and look at that, there's has to be really the, sort of like the vacuum versus a medium. It turns out that it's the speed of light in vacuum divided into the speed of light in a medium. So looking at both of these, we know that the lawnmower tells us about the speed. Now the index is telling us about this electricalness. So then what this tells us here is that it really says that this is the speed of light divided by the speed in the medium times n. So if we rewrite this, here's what we find, that the speed in a medium is equal to c divided by the index of refraction. Now, we got to be careful with language. The language can get really, really tricky. The speed of light in a medium is called the apparent speed of light. And this is what we call the apparent speed of light. since n, the index of refraction, is always at least equal or greater than 1, then the apparent speed is always slower than c. So if you look at this thing, and if you look at the apparent speed of light, here's what we're really saying here. So if this is the apparent speed of light, it's equal to c over n, but you can see here, the speed of light is a constant, so that's equal to 1 over n. So what are we really seeing when we look at this thing? Well, if I have a larger n versus a smaller, then what that tells me is that I have more electrical interaction. And if I have more electrical action, I'm then going to have a lower, and I'm going to run out of space. So let me back off this thing. I'm going to have a lower apparent speed. Which then tells me that Vn is going to be less than C. However, if I have a smaller index of refraction, that means I have less electrical interactions. So therefore, I have a higher apparent speed, but that speed is, even though it's higher, it's still less than the speed of light here. So to give you a sense of what this all is telling me here, I want to show you a table of values. So here is a list of index values for light with wavelength 589 nanometers. And you'll see that that becomes important. So what am I seeing here? So here's my table. And what you're seeing here is that I have a medium. There's vacuum. So if you're at vacuum, you can see that the index of refraction is 1. And therefore, the speed of light in vacuum is c. Air, you can see here, it's as close to 1 as you could possibly get, but it's not exactly 1, but it's pretty damn close. So we typically say that the index of refraction of air is the same of vacuum, and we give it a value of 1. Now, if you go to water, you could see that the index of refraction is increasing. And if you go all the way to acrylic glass, you could see that it's really increased. And you can go all the way to diamond or glass. There's different glasses that have that. So what you're seeing here is that if I have, so if I now look at how does the apparent speed show up in refraction? Well, here's what we know. I need 2 mediums, okay? And so let's say that I have this medium right here. And if I look at this medium, and that's my normal right there, I could imagine that this guy might be, I don't know, let's call it glass. So if I look at glass, let's talk about acrylic glass. Acrylic glass tells me that this is the speed change due to this index of refraction right there. So if I come in, I have a light ray coming in, and if let's say that this is air, and now this is N of glass, which is in this case, I'm going to say is 1.49, then what's going to happen is that this guy bends more than, let's say, water. So now if I do the exact same type of thing over here, and let's say that in this situation, we have a different index of refraction. Here, again, we have N of air. Here, we're going to say that we have index of water, and index of water is 1.33. So when I look at this guy, what do I actually see? I see that the light ray comes in, but now the refraction is not as steep here. Well, that didn't do very good. Yeah, it's going to look something like this here. But if I look at my red, you could see that there is a refraction at this point. And so what you're seeing here is that the larger the refraction, in this case, I see that N, which is then going to be 1.49, that's also equal to the apparent speed of light divided by c here. And that number, wait, let me make sure here. I have this reverse. So if I look at, so for n equal to 1.49, that tells me then the apparent speed of light compared to that in vacuum, I get a value of 1.67. So that means here that it's 67%. Is that 67%? Yeah, it's 67. So that's 67. I'm talking about acrylic glass. That means here that this is 33% slower in acrylic than air. But if I look for water, then that tells me that the ratio of Vn to C, now look at where water is at. This is this guy right here. You could see here is that for water, this guy is actually what? This value is 0.75. So this tells you that it's 25% slower in water than air. So you could see that it appears that there is a decrease in this. Now, one last thing before we end this chapter, I want to start talking about something called the total internal reflection. So what I want to do here is that I want to start with an image, and then we want to actually, maybe we should start with the applet first and then go from there. So let me go make sure that I have my applet set up. which I do. So let me go share my screen. And here's the applet that we're looking at right here. So what I'm going to do here is that I wonder if I could bring this all the way down. I don't think I can. So we're going to have to do it from here. So one of the things that I want you to pay attention is that the light is going from a higher index. Let's say if we made this water right here. Nope, let me change the angle of this guy. Let's say that I make this of water right here. So the first thing that you should look here is that if I start perpendicular to the surface, Snell's law says that the angle of refraction is 0. So there's no refraction at all. But now, if I start at a higher index to a lower index, and I start to move it, one of the things that you're seeing here is that this ray is, as I move it, you can actually see that this ray, this refracted ray, is bending away from the normal here. So if this is, let's say, at 45 degrees, let's see if that's 45 degrees. That's pretty close to 45, right? That looks like 45 to me, or pretty damn close. You could see that the refracted angle is not at 45, but it's higher. Now, as I continue to move this thing lower and lower, look how the ray is approaching the boundary. So as it approaches the boundary, look what I'm going to try to do here. At one point, this is going to be real tricky to, if I wish I could just do it so slow. What you're seeing here, oops, I'm going the wrong way. If I could just bring it to the surface here. And look what happens. Look how this ray, the reflected ray, is very bright. The refracted ray approaches the boundary and it's getting dimmer. And what you're going to find here is that if I'm at the critical point, you'll see here that the ray has disappeared. When it has disappeared, this is called the critical angle of total internal reflection. Now, let's go look at this in detail in my notes so that I could try to explain it. Here we go. So I have an old image, which I think is a good image, and I'm going to use this. And it goes something like this. So we already know Snell's law, but here's what we have here. So I'm going to paste this right here, and let's start to answer what are we seeing here. So one of the things that you're seeing here is that if it's at 0 degrees, there's no refraction or reflection if it's at 0 degrees. But what you're seeing here is that now, in this situation, you're seeing this here. 1, you're seeing that the incident light starts at the higher index and refracts into the lower index. And one ray that you're seeing here is that if I pick this particular ray here, let's say that I look at this one, let's say at 30 degrees, what you're seeing here is that I'm going to have a ray that comes like this, and then this here is my unrefracted ray. And now what you can see here is that this guy right here is now bending away from the normal. So I'm seeing that this ray is actually bending in this direction like this. So at the boundary, there is partial reflection, refraction. Now, 3, at the critical angle, the refracted ray is at 90 degrees on the boundary. So if I look at this guy, so if I look at this one at the critical angle, this is the critical angle right here. You see that this ray is now moving along the boundary. So what you're seeing here is that from here, this angle here, this is 90 degrees. And then this angle from here to here is what they call the critical angle. So then we then say here that for any angle greater than theta critical, still internally reflects. So if I pick another ray here, let's look at a different colored ray. How about if I pick this blue right here? That what you're seeing here is that this guy's coming in here. Try that one more time. And you could see here is that this guy just critically reflects. And this angle here, this angle is greater than the critical one here. So what does Snell's law says here? Snell's law says something like this. From Snell's law, we have that N1 sine of theta 1 is equal to N2 sine of theta 2. So in this situation, we must have N1 greater than N2. So because of this, theta 2 is the refracted, and when theta 2 is 90 degrees, then that tells us here is that theta 1 is at that critical point where all light gets reflected. So now if I put this all together, we then say that this is N1 sine of theta critical. Then I'm going to get N2 sine of 90 degrees, but we know that sine of 90 degrees is 1. So then that tells us here that theta critical is then going to be the sine inverse of the index values where N1 has to be greater than N2. Now, it's super important that if N1 is smaller than N2, then you're going to get a mathematical error because now you're saying that sine of theta is greater than 1, which is impossible. So two values that are important, so two common values of total internal reflection goes like this. One of them is for the air water interface. So if you do that, you're then going to get the critical angle is then going to be sine inverse of the index of air divided by the index of water. And if you put these numbers in, you're going to get the sine inverse of 1.33 divided into 1. And that value tells you that it's 48.8 degrees for the critical value of air-water boundary. Okay, that's one important value to remember. And the other value is that you have the air glass interface. So in this case, we're looking at the sine inverse of air. Oops. And if I plug in my values again, I'm going to have that this is 1.52 versus 1. And if I compute that number, it becomes 41.1 degrees. And this would be theta critical for air and glass. So let me just show you a couple of images here. So if I look at this image, here's a total internal reflection. So what you're seeing here is that you're seeing a ray that's doing what here? Let's see, is this going to show up well? I think so. So I'm going to look at it this way. So it's going to come in. Wow, I can't tell how it enters. It looks like it enters somewhere around right here. Okay, and then what you're seeing here, wow, that's a hard angle for me to see here. Well, guess what? It's not supposed to enter there, that's why. That's why I'm having trouble. You have to start at a higher index of refraction. So we're shooting this and it goes like this. So here's where you start. And then what you're seeing here is that there's a total internal reflection. So let's say here is that this is air, and let's say that here that this is acrylic. Then I'm seeing here that if this is my normal, then this angle is the same as that angle, but I'm starting from inside. Another really beautiful image on total internal reflection is of this turtle. Look at this turtle here. The turtle can't see out of the water because it's at the critical angle. The light starts in the water and it stays in the water because it's at that critical angle.